Today we're going to look at features of polynomial graphs. So we have been reviewing quadratics and their graphs, and they are a type of polynomial, but now we're going to talk about what if it's more than just a quadratic? What if it's a cubic, quartic, quintic polynomial? So let's first review that polynomials are written in standard form when the powers of x are decreasing and our constant term is last. This is what you're used to seeing when presented with a polynomial or working with a quadratic. So number one, f of x equals 10x minus 6 plus x cubed minus 8x squared. So first, let's talk about putting it into standard form. So if I have f of x equals standard form, highest degree or exponent first, x cubed, and working our way down. Now minus 8x squared plus 10x minus 6. Now it's written in standard form, and we can answer the rest of these questions. What is the leading term of the polynomial? The term is the entire piece that's added or subtracted in our polynomial. Now that we've put it in order, it's x cubed. Second question, what is the leading coefficient? So we're still looking at that leading term. That leading term had an understood 1, so our leading coefficient is 1. What's the degree of the polynomial? So the degree is going to be your highest exponent seen in your leading coefficient. So when we put it in standard form, our degree was 3, or this would be a cubic polynomial. And then what is the y-intercept? So two things I could do here. One, I could just look at the constant term is going to be the y-intercept, or where this graph crosses the y-axis. Second thing I could do is I could plug in 0 for x, because if we're talking about a y-intercept, the x value is always going to be 0. So if I wanted to, I could plug in 0 for x to find the y-intercept. But for this one, like I said, we can just look at that constant term, which is negative 6. Let's go again for number 2. Number 2, f of x equals negative 2x to the 4th minus 3x squared plus 2x plus 7x to the 5th, almost in standard form. So let's rearrange it. Highest exponent or highest degree, working our way down, 7x to the 5th minus 2x to the 4th minus 3x squared plus 2x, and that concludes our polynomial. What was that leading term? What is that front term there? 7x to the 5th. The leading coefficient there is 7. We saw that when we put that in standard form. What's the degree of our polynomial? A 5. It's a 5th degree polynomial. And then what is the y-intercept? Now this time we didn't have a constant term, so I would have to plug in 0 for x to evaluate. So let's talk about that for a minute. As I plug that into my polynomial, let me use function notation here. Plugging in 0, we have 7 times 0 to the 5th minus 2 times 0 to the 4th plus 3. Do you see what might be happening here? Minus 3 0 squared plus 2 times 0. Ran out of room there. What's happening there? We've got 0, 0, 0, 0. What is our y-intercept? 0. So this one will cross right through the origin, honestly, of our coordinate plane for our polynomials graph. For our next part here, let's look at this table and use it to talk about how our polynomial graphs may look. Let's start with looking at our leading coefficient. If the leading coefficient, we just talked about that terminology above in those problems, that leading coefficient, if it is greater than 0 or if it is positive, we already know this from our study of function transformations from quadratics. If it's an even degree, let's say our most basic, y equals x squared, your nice happy parabola, right? We had this beautiful smiley face parabola. If a is less than 0 or it's negative, if our leading coefficient was negative, what happened? It reflected over the x-axis. So let's still talk about our quadratic parabola. It just gets flipped upside down, right? Let's talk also about, let me switch colors here. If our leading coefficient is positive, but it's odd degree, so a little bit of new here. What if we keep it simple, y equals x cubed? If it's an odd degree, now this could be x cubed, x to the 5th, x to the 7th, and we'll talk more about that here in a second. But x cubed makes a cute little shape like this. Isn't that precious? Notice it is going up from left to right. am mentioning that because our leading coefficient is what? Positive. Okay? What if the leading coefficient is negative? We know this from function transformations. That beautiful shape that I just made for you is going to reflect across the y-axis. And we saw cubic functions in our transformation lessons as well. Notice it's going down from left to right. And why? Well, it's got a negative leading coefficient. So what if it wasn't just y equals x squared? What if it is another even degree? What if it's x to the fourth? Let me list some of these. What if it's x to the fourth? What if it's y equals x to the 18th? If it is even, an even value as the degree, it's going to have the same rules here. We're going to have both of our arrows pointing up. There just might be some extra humps and bumps. So both arrows are still up. Just our polynomial might have some extra humps and bumps, okay? Same thing if our leading coefficient is negative, as long as we have an even degree, both arrows are down, we just might have some extra humps and bumps along the way. Guess what? Same is true with odd. So I graphed in orange the cubic function as just a parent function, but if it's odd and leading coefficient is positive, left arrow is down, right arrow is up, could have some extra humps and bumps. Negative leading coefficient, odd degree, left arrow is up, right arrow is down. Could have some extra humps and bumps. And we'll talk more about those humps and bumps along the way, but this is our general pattern using our leading coefficient and looking at our degree, whether it's positive or negative leading coefficient, even or odd degree. Okay, so let's look at an example right below. Use the graph shown for the following questions. Is the degree of the polynomial shown even or odd? So I'm looking at our arrows here going opposite directions, opposite, odd, right? So this is an odd polynomial. I don't know if it's a x to the cubed, fifth, seventh, ninth. I don't know, but I know it's odd. Is the leading coefficient positive or negative? It is going down from left to right. So I know that its leading coefficient has got to be negative. Do you see that mimicked above in our table? Question C, zeros are where our graph touches the x-axis. We've already studied this. We've talked about this vocabulary with our quadratics. How many zeros are there? How many times does the graph cross or touch the x-axis? Let's do blue for our zeros. I see 1, 2, 3, 4 places where it cross touches the x-axis. D, relative maximums are any high points, and that is relative to the points around them. So if you've got a point and the two next to them are both lower, that's a relative maximum, not extreme maximum. We'll talk about that in a second. So how many relative maximums are there? There's a high point here and a high point here. There are two relative maximums. Relative minimums, same concept. Low places where its neighbors are higher. We've got a low place here, 1 and 2. Relative extremes. Now, these are terms that Delta Math uses. So when it says relative extremes, it's asking about both those minimum and maximum points. I should be able to add my last two questions together. The 2 plus the 2 should make 4. And let's double check. Low, high, 4 places. On page 2, we've got another example, same setup, using the graph. Answer the following questions. Is the degree even or odd? Looking at my endpoints there, they are going the same direction, similar to our happy quadratic. So this is an even degree polynomial. Is that leading coefficient positive or negative? Both arrows are up, so therefore positive leading coefficient. You can look back at your table and see that correlation. See how many zeros are there. Zeros are where we hit or touch the x-axis. I see 1, 2, 3, 4, 5 zeros. How many relative maximums? 1, 2 high places. Relative minimums are low places. Don't miss this one. There's 1, 2, 3 relative minimums. And then relative extreme values, all of those. Any high and low places, we had 1, 2, 3, 4, 5 total high and low added together on that graph. The next part is actually review. We've done this section before. The graph of a function f of x is shown. Identify the interval as positive or negative, and then increasing or decreasing. So 2 different questions here that we're going to label. A, what is true about the graph from point D to E? So here's D to E. It is increasing, but it is negative because it's below our x-axis. So it's a negative interval increasing. Let me add that over here as well. B, what's true from C to D? C to D also is below our x-axis, so still negative, but that interval is decreasing from left to right. Point C, or question C, from points F to G is over here. That's above our x-axis, so positive, and it is falling from left to right, so decreasing. And then the last one, don't forget we can use that interval to show those endpoints. So from G to infinity, so towards the end of our graph there, it is above the x-axis, so still positive and increasing. Okay, so hopefully you recall that from a couple weeks back. And last section here is end behavior. So end behavior describes what happens to a graph at the extreme ends of the x-axis, meaning to the left or to the right. Notice our notation here. X approaches negative infinity. That's the left side. Negative infinity is always on this side of our x-axis. And you read that as x approaches negative infinity. The next part, x approaches infinity, is to the right, towards positive infinity, the positive side of our x-axis. So that's the right side. Let's identify the end behavior for each graph below. In this first one on the left, our notation here says as x approaches infinity. That is to the right. We are going to answer the question, what is happening to our y values? So I'm looking at the right side here. As x is approaching the right, what is the y value doing? The y value is going down or is approaching negative infinity. So the part that we are filling in is that negative infinity piece right there. Below that, we have as x approaches negative infinity, which is the left. So looking at our left arrow of our graph, we are being asked, what is the y values doing? As x goes towards the left, that y is clearly going up, up, up towards infinity. So we are filling in that piece right there. Y approaches positive infinity. I believe on Delta Math they have multiple choice, and it shows all of this together as a multiple choice answer, like as x approaches infinity, y approaches negative infinity, as x approaches negative infinity. So just slow down and read through it and identify, okay, we're talking left. Where's the y going? We're talking right. Where's the y going? Okay, let's try one more time. On the right graph, first we're asked as x approaches infinity to the right, what is our y's doing? So looking at that arrow as it keeps going right on the x-axis, it is clearly going down. So our y values, oh, look, they used a different notation. This is just another way to write y, right? So f of x is approaching negative infinity. As x approaches negative infinity, as we go to the left, what are the y values doing? Looking at that left arrow, it's going down as well, correct? So f of x approaches negative infinity. So that's the beginning of our introduction, features of polynomial graphs. We looked at some basic vocabulary from Algebra 1, looking at our polynomials in standard form and looking at leading term, leading coefficient, degree, y-intercept. We use those features, leading coefficient, degree, to talk about the shapes of polynomial functions. Based on the degree and leading coefficient, their arrows always go a certain way and have a certain shape. And so we were able to answer the following questions with the degree, leading coefficient, zeros, relative extreme values. We reviewed those intervals of increasing, decreasing, positive, negative, and lastly, introduced to you in behavior. So as you have questions, guys, let me know. And next lesson, we'll look a little bit closer at these graphs of polynomial functions. I'll see you in class.